last tutorial, we'll solve problems from different chapters. That is, there will be miscellaneous problems. So the first problem says which two of the following spaces are homeomorphic to each other. Mainly those problems are taken from NBHM exams. Okay. The first one is given by x times y equal to 0. So graphically it represented by x and y axis. This is one. Second one says x plus y equal to 0 and x plus y equal to 0 and xy equal to 0. So xy equal to 0 is represented by this hyperbola, this with this, but we are considering x plus y is greater equal to 0, that is the part which is in this region, right? Therefore the given curve will be, I need to erase this part. So this is the given curve, y equal to 1 by x. Now let us draw the third one. Here x times y equal to, here x times y equal to 0. That means it is actually this part. X y equal to 0 means it is x axis and y axis, but only we need to consider this region because of the fact x plus y greater equal to 0. So only this is the remaining thing. Now xy equal to 1, this is the hyperbola, rectangular hyperbola, and it can be given by those two portions. So I can remove this part, but it is okay. And problem number 4, here x plus y, this additional condition is given. That means we need to consider that first word. So only this part will be there, right? So those are the curves. Those are the given region. Now we need to see which of the followings are homeomorphic. We can see that this curve, this is actually homeomorphic to real line, right? This is homeomorphic to this real line R. How can you see this? Just take this as positive 0 to infinity and take y-axis as negative 0, infinity. This will be the homeomorphism. Okay. So explicitly, if we try to write, then x comma y, send x comma 0 to x and 0 comma y to minus x. So this will be homeomorphism. This is our f, and the inverse image f inverse send x, f inverse x equal to x comma 0 and 0 comma minus x. This is for x greater than equal to 0. This is for x less equal to 0. So those are continuous. Piecewise, those are defined and they are agreeing at the intersection. Therefore, those functions are well defined and continuous. Intersection is closed, so there is no issue. Similarly, we can prove that this one is also homeomorphic to R, because of the fact we know that x is homeomorphic to graph of the function, graph of a function g. So gf means it is given by x comma fx. This kind of pair belongs to x cross y such that uh, here f is continuous. That is the consideration. So this is the graph such that x belongs to x. This is, otherwise it represents a point. So x and graph of x is homeomorphic. So this one can be thought of as, if we consider the domain open 0 to infinity, then x in this case take x equal to open 0 comma infinity. So g, this is our GA, this curve. Therefore x is homeomorphic to GA. And moreover, open 0 comma infinity, this is homeomorphic to R, right? Therefore those two are homeomorphic. 2 and 4 both are homeomorphic to R. Open 0 comma infinity, this is again homeomorphic to R. Therefore this is homeomorphic to R and 2 is also homeomorphic to R. So 2 and 4 are homeomorphic. Answer is 2 and 4. But what about x1? So x1 is this. This cannot be homeomorphic to this, right? Because if we remove the point, then it breaks into 4 disconnected components. But here, if we try to remove a point, it will break into two disconnected components, right? Similarly, if we remove any point, there will be two disjoint parts. There will be two connected components. Sorry, not disconnected, connected component. And 3 is also not homeomorphic to 2 because it is already disconnected. There are two connected components. 2 and 4 are homeomorphic. 3 is not homeomorphic to 2, 4. So this is a class. Those two are homeomorphic. Another class will be 3. Another class will be 1. And 1 is only homeomorphic to 1 because 1 cannot be homeomorphic to 3. It is already disconnected, right? So all those are, only 2 and 4 are homeomorphic in this question. Now what about this? Which of the following spaces are compact? So we know by Hahn-Borel theorem if we consider Rn with usual topology, then a subset of Rn is compact if and only if it is closed and bound. Right? This is the statement of Hahn-Borel theorem. So to see something is compact or not in R2, we need to see if that is closed and bound. If we consider the first question, mod x plus mod y less than 1, less than 10 to the power something, this can be drawn as this picture. Mod x plus y, that is x plus y less than something, and since mod arises, so there will be 4 line, and this is the region. But one can see that it is not closed. Boundary is not there actually. need to erase the boundary. Right? Boundaries are not present. So this is open and not closed. Something cannot be both open or closed because that will imply that will open and simultaneously open and closed will imply it is disconnected because we are taking non-trivial subset. So it is open. It is not closed subset. Not a closed subset. For one, this is not a closed subset, therefore not compact. Why this is not a closed? Because we can see that take a point from the boundary, every neighborhood intersects the region, but those boundary points are not present in the domain. Right? So this is not compact. Not closed means not compact. Mod x plus mod y less equal to 10 to the power 100. In this case, the region will be given by similar kind of picture, some big picture, but I am not maintaining the scale. So it will look like this, but in this case, boundary will be there. This is the region, right? So it is closed and bounded. Closeness is clear. Take any point. So if we take a point from its complement, then there exists a neighborhood which entirely lie in the complement, right? Therefore, it is actually closed, and boundedness is already there because this is contained in some finite radius open. If we take an open ball from the with whose center is at origin, then entire rectangle is containing this open ball. Therefore, it is bounded. So closed and bounded, that imply it is compact. Okay. Option 3. In this case, x square plus y square is less equal to 2. That means it will be less than some. It is containing some circle. The region will be given by those two concentric circles. Okay. So this is the region actually. This part. This is again closed. It is closed, and boundedness is also clear. Why closed? Again, if we take a point from the complement, then there any point, then there exists an open neighborhood which contain in the complement. So those are closed and bounded. Therefore, it is compact. For those kind of problem, another way to see something is closed or not. This can be if we consider this function fx comma y equal to x square plus y. This is a continuous function from R2 to R, and this domain, it is given by f inverse closed 1 comma 2, right? F inverse closed 1 comma 2. So this is closed in R, therefore its pre-image will be closed in R by continuity. This is how we can also check continuity of if something is continuous or not, something is closed or open. Now for option 4, here x square plus y square equal to 1 and xy non-zero. It means it will be the circle, but xy non-zero means we need to remove the parts which are in the which lies on the x-axis and y-axis. So there will be 4 segments like this, 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 and this. So the points on x-axis and y-axis are not there by this condition. Now it is clear, though this is bounded, this is clearly bounded but not closed. Why it is not closed? Because if we take, sorry, okay, this is not closed because if we take this point, then every neighborhood will intersect the region, given region. Therefore, this is not closed and hence it is not compact. So the only correct options are this and this. 1 is not compact, 4 is not compact. So let us see question number 3. On which of the following spaces is every continuous function bounded? Real value continuous function. So for 0 to 1, we know there are lots of functions which are not bounded if the domain is 0, 1. For example, counter example of 1. Consider fx, f from open 0, 1 to R, where fx equal to 1 by x. So this is not continuous. Means, sorry, this is not bounded. This is all obviously continuous because the 0 is not there in the domain. Okay. Now what about the second one? If we consider x2 equal to closed 0, 1, so second one is okay. Why? Because x2 is compact, closed and bounded, therefore compact. Hence, f of closed 0, 1, this is also compact. Image of a compact set under continuous map is compact. This is compact since f is continuous, right? And we know if something is compact in R, it is bounded. And compact subset of R is bounded. So 2 is okay. It is bounded. Any function from close 0, 1 to R will be bounded. For 3, again close 0, open 1. We can consider lots of counter example. Counter example, take fx, define fx equal to 1 by 1 minus x. So this is continuous and it is unbounded, right? When x tends to 1, if it tends to infinity, f is unbounded. This is unbounded. For 4, here t is irrational, so we can consider the same counter example 1 and 3 both will work. So take fx equal to 1 by x. Note that 0 is not there in the domain because 0 is rational. So we are only considering the domain is Q complement intersection close 0 1 1, right? This is the domain. So it is clearly unbounded. As x tends to 0, it tends to infinity. So only correct answer is 2. For question number 4, here a is given by x minus x0, where x0 is a point in x. Now a is open, closed, connected, or dense. Which of the following is true? So note that the topology, it is Hausdorff space. X is Hausdorff. Therefore, Hausdorff means T2 condition. T2 will imply T1, and T1 imply every point is closed. T1 is true if and only if every point X is closed. Right? So that singleton set x0 is closed. Therefore, x minus x0 is open. So this option is okay. This is open. Now, what about closed? Closed may not be true for arbitrary Hausdorff space. So closed will not be true. Take R minus singleton set is 0. So this is not closed in x equal to R. This is a counter example. What about connectedness? Again, same counter example. R minus 0 is disconnected. So connected may not be true. Take R minus 0. What about density? So in this example, R minus 0, this will be dense. Closure of R minus 0 will be polar. But this may not be true in general case. Take x equal to any discrete topological space, R with discrete topology. Then every set is closed and a equal to R minus 0, then closure of a equal to a itself, because everything is closed, everything is open in discrete topological space. Therefore, it is not dense. A is not dense in X. We need to find distance between those two topological space. Let us draw the picture. So one space is given by y equal to 0. Y equal to 0 means it is this x-axis. Now another space, this is our A, and another space is x comma y such that xy equal to 1. So this will be our hyperbola, xy equal to 1, this part. Right? There will be another branch like this. Okay. So we need to find distance between this B and A. This is B. So we know the distance DAB, this is defined as infimum of dA comma B, where A belongs to A and B belongs to B, right? Now, if we consider only those points, so take some points, for example, n comma 1 by n and another point n comma 0. Then distance, so this is, consider this is uh, bn and this is an. Then d of an comma bn, distance is given by this formula, n minus n square plus 1 by n minus 0 whole square, right? This is the distance in Euclidean metric. So this is actually 1 by n. Therefore, infimum over all such A belongs to A and B belongs to B must be 0, right? Because infimum is always less equal to DAN comma BN. Infimum DAB, this is less equal to DAN comma BN for all n, which is equal to 1 by n. So this is less than equal to 1 by n for all n. That means this one is 0. Infimum, that is same as distance from A to B, is 0. So note that A and B does not intersect. There is no point which is both there in A and B, but their distance is 0 because they are approaching closer and closer as n tends to infinity. Though they never touch, but their distance is 0. So this is possible because A, B are not yes. This is possible because those are non-compact set. Otherwise, we'll get some contradiction. Okay. Here f is a map from R to open 0 infinity given by fx equal to 1 by x. So we need to see if it is homeomorphism or not. So note that fx equal to e to the power x has a this is continuous obviously, and there is a inverse map. So gy equal to log y. If we try to define the map G from open 0 infinity to on, right? This is well defined because 0 is not there in the domain. This is also continuous, and F compose G is identity, G compose F is also identity. Therefore, for option A, F is a homeomorphism. What about option B? Here, Ft is given by cos 2 pi t, comma sin 2 pi t. So note that there are lots of for f of 0, this is same as cos 2 pi comma sin 2 pi, which is 1 comma 0, and f of 1 is also cos 0 comma sin 0, which is 1 comma 0. This is cos 2 pi sin 2 pi, which is also 1 comma. So this is not even injective, which implies not homeomorphism. Homeomorphism Homeomorphism means it should be bijective and the inverse image is also continuous, but it is not injective, therefore not homeomorphism. Now what about C? In C, it is a F is a continuous map from compact, X is compact, Y is Hausdorff. This is continuous. Okay. So note that F of some closed set. If we take F of some closed set, so a closed set let A containing X is closed. Every closed subset of a compact set is compact. Therefore, A is compact. Since it is a closed subset of a compact set, therefore F of A will be compact. Since F is continuous, image of a compact set is compact. Therefore, F is a closed map. F is a closed map means F inverse, if we take the inverse map, F inverse of closed set is closed, right? Because this is same as F of closed set, which is closed. And this is one of the definition of continuity. Inverse image of a open set is open, or we can also say inverse image of a closed set is closed. This is another way to define continuity. Both are equivalent. Therefore, F inverse is continuous. F inverse is continuous. So we have F and a reverse direction map, F inverse, both are continuous. Note that we have used F inverse. This is possible because of the fact F is both 1, 1 and on 2. Otherwise, if it is not on 2, then we don't have any map in this direction. Right? This F inverse is possible because of 1, 2. Now, injectivity define F inverse properly, because due to injectivity, there is only one choice. We don't have 2 point which goes to 1 point in 1. That's why we are getting a proper F inverse map. And we are only proving this F inverse is continuous. So we have found a map in the reverse direction which is continuous, and F compose F inverse is identity, F inverse compose F is identity. Therefore, F is a homeomorphism. So C is okay. This is not true. This is also okay. We are considering real n by n matrices as the space Rn square. So we know that Rn square, this is homeomorphic to Mn by n. If we consider space of all n by n matrices, then this is homeomorphic to Rn square. Because, for example, if we consider 2 by 2 matrices A, B, C, D, this can be mapped to A, B, C, D, this pair. This is a homeomorphism. So, which of the following are compact? Again, by Hahn-Borel theorem, compact is true if and only if it is closed and bounded. So we only need to see those subsets are closed and bounded or not, those subspaces. So for option A, this is orthogonal set of all orthogonal matrices denoted by n by n. This is a subset of mn by n. So is it a closed subset? How can we check? Consider the map determinant map which sends mn by n to R, right? Maybe a better notation is when R, mnr, something like this. So determinant is continuous map because determinant is just a polynomial of those components, continuous. Now orthogonal matrix is defined by determinant is same as, sorry, orthogonal means A times A transpose is 1. So determinant map will not work. So we consider this map. F of A is same as A times A transpose. Then this is also continuous because this is multiplication. A times A transpose, this is multiplication, and all of those entries are actually in in ijth entry that will be a polynomial of those component A, B, C, D, or there are n by n many components. So this is continuous, and note that F inverse of identity is actually orthogonal matrices. Set of all orthogonal matrices, all such matrices such that A times A transpose is identity. Hence, identity is a singleton set that is closed. No, this singleton set identity is closed because it is already housed out. Therefore, T1 space, hence every singleton set is closed. Therefore, pre-image of closed set is closed. So closeness is okay. We need to see if this is bounded or not. Okay. So the problem will be it may not be bounded. Though this is closed, it is not actually bounded. For example, consider this kind of matrices n comma 1 by n 0 0. Sorry, this is not orthogonal. Actually, it will be bounded. But how can you show this is bounded subset of mn square, mn by n matrices? Okay, we'll check it. Before that, let us see which of these are not compact. So the set of all invertible matrices and set of all matrices with determinant equal to 1. So B is not true. Not true. Though this is closed, using determinant map, we'll get this set of all matrices with determinant 1 is closed. But this will be not bounded. Take n comma 1 by n. So this kind of matrices has determinant 1. It is n by n matrices. Something k comma 1 by k. And every other entries are 1. And those are 0. Then this is actually as k tends to 0, the distance becomes greater and greater, right? So this set is unbounded set. Distance from the origin tends to infinity. If we take this kind of matrices. Now what about C, set of all invertible matrices? It is again not true, because set of all invertible matrices is actually open. F inverse of, so consider the determinant map from MNR to R. This is continuous map, there is no issue. And GLNR, invertible matrices, is given by determinant inverse of non-zero element. So this is R minus 0. This is open set, therefore pre-image of open set is open under continuous map. So GLNR is open, and something cannot be open and closed simultaneously, because Rn Euclidean space or MNR, that is also Euclidean space, is connected. By connectedness, this cannot be closed. So B is false, C is false. What about A? We need to see that the space of all orthogonal matrices, this is bounded. Distance from that is distance between any two orthogonal matrices are bounded. One way to define norm of a matrix is by supremum A times X, where X is a non-zero vector. Norm of this by norm X. Norm X square is same as X transpose times Ax, and A transpose A is identity, that means this is X transpose X. So this is norm X square, norm X by norm X, because we need to take modulo. So from here it is clear norm of A is 1. Therefore, so for A belongs to winner, because of the property we are using this property, right? We can find norm of A is 1. So it must be bounded. Distance from origin is always 1. So all of those orthogonal matrices are one radius, are at most one radius, not at most, it is exactly one radius away from 1 unit radius away from the origin. So this is actually bounded. Those lies in this sphere or this circle, whatever we say. We need to classify the following alphabet into homeomorphism classes. In this case, I will not present any explicit proof. I will just gauge. So if we consider n, from it is clear if we just deform n, it will becomes this, right? It is like unfolding this n. If we just fold this line segment, this will become n. Therefore, n is homeomorphic to this line segment, close 0, 1. Now, what about B? What about H and M? So, let me draw M. So, M is again homeomorphic to this line segment. 1, 2, 3, 4. So, this is this part. This one will represent this part. This one will represent this part. And this one is just fold this line segment. We can fold it into M. Therefore, both are homeomorphic to close 0, 1. Hence, N and M are homeomorphic. So 1 plus will be N comma M. And can H be homeomorphic to N or M? B? Answer is no. Because if we just remove a point, I'll remove this point, then it will break into 3 components. This one and this. There are 3 components, right? 3 connected components. But whenever I remove a point from N or M, this will break into 2 components, whatever point we remove, right? Therefore, this H cannot be homeomorphic to N or M. So H is in a different class. Similarly, B is also in a different class. For B, sorry, here we need a specific drawing. So remove this part, remove this point, remove this point. So B minus, suppose this is P, then B minus this singleton P, it will break into 2 components, 2 or more than 2. Let us see. Okay, it will break into these 2 components. One will be this, another will be this, right? So B cannot be homeomorphic to H, because whatever point we remove, for example this point, it will always break into 3. If we remove this point, it will break into 3 components. But if we remove this point, it will break into 2 components. But those 2 components are not homeomorphic to this type of thing, because this is again homeomorphic to some line segment. but this is not homeomorphic to line segment. Again, we need to remove this point to prove that. So it is B and H are not homeomorphic, B and N are also not homeomorphic by same kind of reasoning. For example, if we remove this point, this will remain connected, but whatever point we remove, N and M will be disconnected. So one class is N and M, another class is H, another class will be B. The set of all n by n matrices with real entries, which of the following are connected? The set of all orthogonal matrices. So we have we have only proved that is compact orthogonal matrices, but here we need to see if it is connected or not. The set of all orthogonal matrices, is it connected? The set of all matrices with trace is unity, the set of all positive definite matrices. Okay. Suppose A is orthogonal. A belongs to ONR. And also assume B belongs to ONR. Then we can show that if we take, so A B belongs to ONR means A transpose is identity and B transpose is identity. And the reverse is also okay, B transpose B is identity. So we'll show that no, that combination will not work if we take the convex combination. Okay, before that, let us consider option B. The set of all matrices with trace equal to unity. A belongs to MNR such that trace of A is 1. So this is the set. So let A comma B belongs to S. Okay. Then we'll prove that any convex combination also belongs to S. So take a continuous map F from S close 0 1 to S given by f of t equal to ta plus 1 minus t. Okay. Then we note that this is well defined. Why? This is well defined because of the fact we need to see that ta plus 1 minus tb belongs to the range S. So ta plus 1 minus tb, if we take trace of this is same as t times trace of A. Maybe write capital TR to differentiate. T times capital TR A plus 1 minus t times trace of B. And trace of A, trace and B, trace of B both are 1. Therefore, this is t times 1 plus 1 minus t times 1. So this is same as 1. So this is well defined and it is always continuous because this is just scalar. Um, this is scalar multiplication. Those are actually continuous functions, and we have taken all those continuous functions and put those functions in components, right? So this will be continuous by definition of product topology. There is no issue. Therefore, there is a path between A and B, right? And the path is given by this function f. Therefore, f is a path starting at A and ending at B. Okay. So S is path connected, and we know every path connected set is connected. So B is connected. What about C? The set of all symmetric matrices, symmetric positive definite matrices. Again, we can apply the same idea. Suppose A comma B be positive definite symmetric matrices. The same idea. We only need to see that this kind of convex convex combination is symmetric and positive definite. So convex combination, that is scalar multiplication of symmetric matrix, is symmetric. Addition of two symmetric matrix is symmetric. So there is no issue. So the non-trivial fact is to see that this is positive definite. So how can we see positive definite? We just multiply x transpose and x, where x is non-zero vector, right? X is non-zero vector in Rn, n by 1. Then this is same as t times. I should not write t because there are lots of t. Instead of t, let me write some 1 minus lambda. Okay, now there is no issue. Let lambda 0. So this is t times x transpose ax plus lambda times this plus 1 minus lambda, just taking common, x transpose bx. Note that x transpose ax greater equal to 0. So this is greater equal to lambda times 0. Lambda is positive and this is 1 minus lambda times 0. So this is 0, greater equal to 0, therefore positive. So 0 is also there. X is a vector in Rn. Positive definite. X transpose Ax is greater equal to 0. This is enough. So any convex combination of A comma P is positive definite. Therefore, we can again consider this kind of path to say set of all positive definite symmetric matrices are path connected. This set is path connected. Any two point can be connected by this linear kind of path. Path connected will imply connected. Path connected which imply connected. So it is remained to show that orthogonal matrix is connected. connected or not. So we consider this function. Consider determinant function from this ONR to R, right? So image of this determinant of ONR is actually plus minus 1, which is disconnected. So image of a connected function under a continuous map cannot be disconnected. Therefore ONR is disconnected. Because continuous function always set a connected set to a connected set. X is an arbitrary topological space, then which of the following are correct? If X is compact, then every sequence. So we know that earlier we have seen compactness will imply limit point compactness. Limit point compactness. And we also know that in metric space, all those are same. Compact, if and only if limit point compact, if and only if sequential compact. Right? So in metric space, all those things are same. But in this case, we need to compare compact set and sequential compact and sequential compactness. So we need to consider those two things, this with this. So in general, this one may not imply another one. Okay. X is compact, then every sequence in X has a convergent sequence. That means X is a sequential compact. So this is not true. Compact may not imply sequentially compact. So consider R with cofinite topology. So we have already observed this is a compact topological space. Why? Because every open cover, open set means it is complement of finite set. So if U alpha be open cover of R, then each of those U alpha only has at most it does not contain at most some finitely many points, right? So for example, suppose U1 does not contains x1 up to xn, then x1, since this is a cover, U alpha is a cover, then there exists U2 such that x2 belongs to U2, and similarly there exists UN such that xn belongs to UN. Then this U alpha, this refines into not refines, U alpha has a finite subcover. We get a finite subcover given by U1 up to UN, right? So R with cofinite topology is always compact. Therefore, it is compact. But it may not have any convergent So instead of considering R, it is enough to consider N. So consider N as a subset of this. Okay. Then we let U alpha be a cover of N. then finally we obtain that we get a finite subcover. Therefore, n is compact. We'll prove that n has no convergent subsequence. Why this is true? Because in cofinite topology, convergent sequence are essentially constant. Constant sequence. It means except some finitely many terms, xk plus 1, all those things are constant. Those are c. Only finitely many terms are allowed to vary, but except those finitely many terms, all those are constant terms. Why this is the case? Because if if those things varies, right? If there are infinitely many terms, distinct terms in the tails, then we can find. So suppose this converges. Suppose let xn converges to some x, right? Then x has a neighborhood x minus this kind of neighborhood x minus sorry some xn. X minus xn is a neighborhood because of cofinite topology. This is open, right? So x has a neighborhood. So if those are different terms, then sorry. For examples, let us see what happens if we consider this 1, 2, 3, this sequence. Suppose this sequence converges to some x. Okay. This will imply every neighborhood of x contains all but finitely many terms of the sequence, right? Except some finitely many terms, all those terms will be contained in every neighborhood will contain all those terms. But for each of the terms, distinct from x, we can consider x minus that particular n. And this sequence and this neighborhood, sorry, the argument is not working actually, but we can prove this fact. Um, Currently, I am unable to prove this fact, but you can check. You can try it later. This will be essentially constant sequence. Every convergent sequence are essentially constant in cofinite topology. So that implies if any subsequence of n, if we take any subsequence that cannot converge. Okay. So A is not true. So A is not true. That will imply C is also not true because C has more stronger statement if and only if. What about B? Every convergent sequence, if every convergent sequence X has a convergent subsequence, then X is compact. B is also not true. B is not true. Why? Okay, B says sequentially compact imply compact. Actually, I am not sure about this question. So let me not solve this question. I am also not sure about this statement. I need to check. Okay, so let us solve question number 11. Here we are considering a continuous function f from S1 to R. So the question is there a continuous function from circle to R which is also 1 1? So option A is not true. Why? Because we have already proved this fact. So if possible, so let us consider the function. Let G map S1 to R defined by G of x equal to fx minus f minus x. Then G at some x is same as, that is G of, if we take G of minus x, this is same as f of minus x plus minus f of minus x, which is plus x, which is same as minus gx. Therefore gx comma g of minus x, those are of opposite sign. So note that this is connected set and the codomain is real number. So we can apply intermediate value property. By intermediate value property, there exists x0 belongs to S1 such that gx0 equal to 0, right? Because intermediate value property says if there is 2 point in the range, then any points in the intermediate points are also attained. That is, there exists some x0 such that f of x0 is same as that intermediate point. Okay, so that's why gx0 equal to 0, but by definition gx0 is same as fx0 minus f of minus x0. So this is same as this. Therefore f cannot be injected. x0 and minus x0, those two are distinct antimodal point of surface. This is x0 and minus x0 is the antipodal point. F cannot be injected. So A is not true. Therefore C is also not true. Because for C there is another extra condition which is on true. But 1 is not even possible. Now B. F from S1 to R, then there exist uncountably many pair of distinct point x and y such that f of x is same as f of y. Let us prove this. So note that f of S1, this is compact, therefore it is compact plus connected. S1 is compact and connected, therefore f of S1 is compact. Image of a compact set is compact, image of a connected set is connected, as f is continuous. Now we know a connected set of real number is interval and it is also compact. Here it is also compact, therefore that must be closed interval. Only closed interval is compact. Other kind of intervals are not compact. There is another choice, singleton set, but that is not possible by the previous question. There are two different points. There should be two defined points in the domain. Sorry. Sorry, that was not the previous one. So there are two choices. If f is constant, we are done. Every point goes to the same point. So there are uncountably many points such that f of x equal to f of y. We are done. If not, if f is not a constant, then so compact and connected will imply f of S1 is a closed interval because it is not compact. It cannot be singleton because we have already assumed this is f is not constant. Okay. So small m is the minima and capital M is the maximum. Image of S1 is this small m comma capital M. Now let y belongs to this small m comma capital M. Okay, by and also assume, now if possible, assume f inverse of y is a singleton point, singleton set. Then what will be the problem? Then note that s1 minus x, if we remove a point from a circle, this is connected. But f of s1 minus x, which is, we have removed the point y from this interval, so this will become m comma y union y comma m. This is disconnected. So connected image cannot be disconnected. Image of connected set cannot be disconnected. This is a contradiction. Contradiction. So therefore there are at least two distinct points which maps to y, and this is true for all y. So from here it is clear that there are at least two distinct point x comma y which goes to same point. So maybe this is z, or any z belongs to this m comma capital M. There are 2 points, at least 2 point x comma y, both maps to z. Fx equal to z and fy is also z. So instead of y, we should consider z. So it is okay. So B is true. In this question, B is closed ball in Rn, closed unit ball, and then the conclusion is there exists a continuous function capital B to R which is 1 1. So A is not true. We have already proved not true. Why? Because F is a map from this closed B to R which is 1 1. 1 1 continuous map. But circle is a subset of B, right? Circle is the boundary of this closed unities. So this gives 1 1 continuous. If we assume that this gives a continuous map F from S1 to R. So if B to R that is 1 1, then if we restrict the map over S1, this is also 1 1, which is a contradiction. We have, in the earlier question we have proved this. There are at least two different points which maps to same. So this is okay. So in previous question I have not said that this is true for uncountably many pairs, and this is why this is true, because M to M, every interval contains uncountably many points. So that's why, and we are choosing Y which is belongs to this M to M. Those Y are distinct. So for each of those Y, we are getting at least 2 points which maps to this Y. That's why we are getting uncountably many points. So A is not true. What about B? There exists a continuous function from B to R which is on. So B is true. If map B to R, Okay, sorry, B2R. This is also not true. Why? Because this is compact. Closed and bounded subset of R2, this is compact. But this is not compact. We know continuous function always send compact set to a compact set. So image of f of b should be compact. Compact implies f of b is compact. But R is not compact, so it cannot be N2. Cannot be onto. There exists a continuous function from B to R which is 1 1 and onto. So C is false because A, B both are false. So none of the above. None of the above. Okay. Here B is given by the closed unit disk and D is the open unit disk. Given a continuous function from B to R, there always exists a map, and there exists a continuous map R2 to R such that F equal to G on B. That means every continuous map from closed disk to R extend to R, extend over R. So this is false. This is true. Why this is true? Because of the fact the domain R2 is normal space, normal topological space. And B is actually closed. So we can use each extension theorem by each extension theorem. G maps B to R extend this continuous map to a continuous map F from R2 to R. Given a continuous map from D to R, there always exists a continuous map from R2 to R which extends G. So this is not true. Why? Because we here note that for B we cannot use Stitch extension theorem because in this case D is not closed, D is open. D is not closed, so we cannot use this extension theorem. But we can explicitly construct a function which cannot be extended further. So G maps D to R. Counter example given by Gxy equal to 1 by 1 minus x square plus y square. That is. So we can see that as we approaches towards boundary, this G tends to infinity, right? When we are approaching towards boundary, this x square plus y square tends to 1. And this tends to 1 implies this tends to infinity. Therefore, we cannot extend G to a whole R. Okay? Because if then that should be bounded. Otherwise, there is no limit. So we cannot extend in the circle. In this, even this cannot extend in this disk, closed disk. In this case, for problem C, F is a continuous map from R2 to R, and we have two sets. One set is x square plus y square equal to 3 by 2. This is one set. Let me denote it by A. And another set is B. B means this closed unit wall. X square plus y square less equal to 1. This is B. With x square plus y square greater equal to 2. Means with this. Those should be, all of those should be circle. Okay. So those are B. So note that A, B both are closed. Both are closed. And R2 is normal space. So by Udison metrization theorem, Udison lemma, there exists a function, continuous function, f from R2 to R, such that f restricted over A is 0. A, B both are closed set, so f restricted over A is 0, f restricted over B is 1. Both disjoint condition is also needed. Otherwise, we may not expect. In this question, given f is a bijection from z to z square, there exists a continuous function from R to R2. So note that if we consider z as a subspace of R, this is actually closed subspace, right? And also we know that z forms a discrete topology. Therefore, this function f is continuous because every discrete, if we take the domain as a discrete topology, then every map becomes continuous. And R is actually a normal space. So again, by teach extension, there exists a function from R to R. This is a subset of R2. So we get an extension. This is our A. In this question, D is the closed unit disk, and D minus 0, 0 to D minus, we need to see if there exists a function D minus this 0, 0 to x belongs to R such that mod x less equal to 1. That means this interval is on, there exists a continuous onto map. Is it true or not? So this is true because what can we take? Define f of x comma y equal to x. So this is our domain, which is disk minus this point. We just remove this point origin. So we are projecting on x-axis. Then this becomes, this is minus 1 0. This is 0 1. So this becomes this interval minus 1 comma close. So B is true. This is a continuous function. Projection is always continuous. What about C? disk minus 0 0 to mod x greater than 1. So f maps minus 0 0 to mod x greater than 1 means minus infinity to minus 1 union 1 to infinity. So we are taking complement of this mod x less equal to 1. So note that this is disconnected, but this one is connected. Image of a connected set is connected, so there cannot be onto function. Cannot be a onto continuous map. Otherwise, we will get a contradiction. Image of a connected set becomes disconnected. Which of the following are correct? F maps open 0 1 to open 0 1 given by this has a fixed point. So A is not true actually. Not true. So the condition is this less equal to condition. This is the problematic part. That's why we cannot use fixed point theory. Take fx equal to x by 2. Then fx minus fy, this is mod x minus mod y by 2, which is equal to this. So this inequality is satisfied, but fx has no fixed point, right? X cannot be same as x by 2. This is only possible when x equal to 0. Only possibility, but 0 is not there in the domain. For the next question, it says f has a fixed point. Okay. For b, we can use we can construct a function and we'll use intermediate value property, right? So let g from gx equal to fx minus x. Then we note that g of 1, this is same as f1 minus 1, right? But range is codomain is minus 1 comma 1. So f1 is less equal to 1 and greater equal to minus 1. So this is less equal to 1 minus 1, which is 0. And g of minus 1, this is f of minus 1 minus minus 1, which is plus 1. But f of minus 1 is greater equal to minus 1 and then plus 1. So g1 so if possible assume there is no fixed point. So it is okay. There is no such need. You can say in this way also. So if g1 equal to 0, it is less equal to 0. If g1 equal to 0, we are done. f1 minus 1 becomes 0. So f1 equal to 1. If g of minus 1 is 0, then again we are done. We'll get f minus 1 equal to minus 1. If g1, then if those are non-zero, then we can consider this case. So if g1 equal to 0 or g of minus 1 equal to 0, we are done. If not, then g of 1 is strictly less than 0, g of minus 1 is strictly greater than 0. We can use intermediate value property to prove, to say there exists some x belongs to this minus 1 comma 1 such that g of x equal to 0, right? And gx equal to 0 imply fx minus x equal to 0, that is fx equal to x. Now for option C, f maps R to R is a continuous periodic function with period t. So again so it is clear B is true, A is not true. So we construct a function gx equal to fx minus this f of x plus t by 2. We note that g of t by 2, this is same as f of t by 2 minus f of t by 2 plus t by 2, which is t. By periodicity, this is same as f of 0, right? So this is f0, ft by 2 minus f0. So this is actually minus g0, right? So g0 and gt by 2 has opposite sign. g0, gt by 2 have opposite signs. IVP imply there exists x such that gx equal to 0. And again, gx equal to 0 means fx equal to fx plus t by 2. So C is also correct. There exists a continuous function f from R2 to f from this set to R, which is 1 1. So 2x square plus 3y square by 3y square equal to 1. This domain represents an ellipse, right? X square by 3 plus y square by 2 equal to 1 by 6. This is equation of an ellipse. But we know ellipse is homeomorphic to circle. Just deform properly, then we will get a homeomorphism. Okay. One way to get the homeomorphism is just use those kind of ray. If we try to write explicitly, then send this point to the corresponding point. Okay. So this will give me a homeomorphism, explicit homeomorphism. But idea is clear. This must be homeomorphic to this. So we need to see there is a map from this ellipse to R, which is 1. If there is a map from this ellipse to R, which is 1 1, then we get a map from this circle to R, which is also 1 1 map, right? If ellipse to R is 1 1, this will imply this is homeomorphism to the circle S1. So we get a circle to R which is 1 1. But we know this is not possible. This is a contradiction. We have already proved there cannot be any 1 1 map. So this is false. There exists a continuous map from -1 1 to -1 closed one which is both 1 1 and on. Okay. Note that a continuous function, 1 1 continuous function is monotonic. Continuous function is monotonic. Again, this is we can prove this using mean value theorem. Okay. For example, if we, for example, let f of x less than fy, so let x less than y, and y is greater than y is less than z, but this is not monotonic. Then what kind of contradiction will we get? Then let w belongs to this fx comma fy, and w also belongs to fz comma fy. Take a neighborhood from neighborhood of fy. Take a point from the neighborhood of fy, which belongs to both of these. Then mean value theorem implies there exists x0 such that f of x0 equal to w, and there exists another y0. So x0 is taken from xy and y0 is taken from yz, or maybe z0. Let me write z0 from yz such that f of z0 equal to w. But this is not possible because of injectivity assumption. So from here, the observation is clear that one continuous function means it will be monotonic. Now, what what will be the problem? We'll prove that there does not exist such kind of function. What will be the problem? The probability part is 1. So if f inverse of 1 is x, then what is the problem? Fx equal to 1, but which is from minus 1 1. This implies for all y greater equal to x, greater than x, fy is greater equal to fx, which is 1. Right? So, but fy is always strictly less than 1. Fy is, but fy less than 1. So less equal to 1, the codomain is minus 1 comma 1. So that means fy should be 1, because fy is greater equal to 1, less equal to 1. Therefore fy is 1. But this is contradiction to injectivity. So B is not possible. What about C? There exists a continuous function from this y square equal to 4x, which means a parabola, to R. Okay, C is true because we have already observed y square equal to 4x is given by this graph, and graph is always homeomorphic to the domain. Domain is actually x. Domain is R. we are considering the function R2, this R2 given by x goes to 4x comma y square. This is the graph. So this will be homeomorphic. This is continuous function, therefore R is homeomorphic to graph of this function. This is GF. So there is a homeomorphism more than just an injective continuous function. There are several more questions. So I'll solve this. This will be the last question. Okay, let me solve. So which of the following are connected? R2 minus Q cross Q. Is it connected set? So the answer is yes, connected. Why? Note that if we, so this is our R2. If we remove countably many points, Q cross Q, this is countable set. Countably many points. Then we'll prove this remains path connected more than connectedness. How this is connected, the path connected? So consider one point. Consider x and y belongs to R2. So this is our x, this is y. So we have only removed countably many points. But note that at x there are uncountably many straight lines. At this point x, there are uncountably many straight lines which contains x. Similarly, at the point y, there are uncountably many straight lines. So, except countably many, for example, this line may contain some point from Q cross Q. This content, but not all those lines, because there are uncountably many lines. So, there are two different lines through these 2 points which must intersect, because we are getting uncountably many lines, and there are also uncountably many lines which avoids those Q cross Q, and all of those lines will intersect each other. So this is path connected by those linear path, hence connected. B, x comma sine 1 by x, and the origin is also there. It will look like this. Something like this. Okay, it will become tensor. So we know that x comma sine 1 by x, this is a graph. Therefore, this will be always connected because the domain is this. Domain is connected, so graph becomes connected. It is actually homeomorphic to this domain, open 0, close infinity. So that part is connected, but 0, 0, that is taken from this, that is the origin. Origin is counted. Now, we observe that 0, 0, that point belongs to closure of this set. So this is S. This part is S, sine curve. So 0, 0 belongs to closure of S. So So since S is connected, if we add some limit points, this will remain connected. S union 0, 0 is also connected. So behavior of connectedness, that is, if something is connected, if we add limit points, this remains connected. What about C? In C, we are considering xy equal to 1. So again, this kind of thing. But union y equal to 0. Y equal to 0 means this x-axis. So it can be easily seen this is disconnected. There are three components, 1, 2 and 3. Three connected components. C is disconnected. Which of the followings are path connected? So for B will look like this kind of x equal to n by ny. So there are lots of straight lines passing through origin, right? Clearly this is connected because all those straight lines are already connected and there is a common point which belongs to all those straight lines. So B is connected. What about A? For A it is given by x square plus y square is equal to 1. We are considering this part and we are also taking y equal to 1. Y equal to 1 means this tangent. So note that this is actually connected because this point is already there and this is moreover path connected. Whatever point we choose, we can always construct a path by convexity. This point we can always construct a path from this one straight line segment that will work. So this is path connected, we simply connected. Set of all symmetric matrices whose eigenvalues are non-negative. For C, we are considering symmetric matrices, and we are also assuming eigenvalues are non-negative. So again, this is easy to see. Take convex combination, and the eigenvalue will be non-negative. No, that is actually not working because we don't know about eigenvalues of arbitrary convex combination. Only polynomial. For polynomial, we can compute eigenvalues. So how can we do this? Here we are considering symmetric matrices with positive eigenvalue. This is the subspace of M&R. cannot solve it right now. Maybe you should give it a try. I don't know. Probably the answer is yes. So A is connected, B is connected, but I don't know about C. Probably this will be connected. The subset of nilpotent matrices are closed in MNC. So this is true because uh, if we consider nilpotent matrices, so nilpotent matrices are defined by all A belongs to MNC such that A to the power k equal to 0 for some k. K belongs to n. Not yes. So why is it a closed subset of MNC? Suppose AN is a convergence sequence. Convergent sequence of nilpotent matrices. This will also not work actually. Here we cannot use those kind of pre-image kind of idea. For example, f from this MNC to MNC given by A goes to A to the power k. This kind of idea cannot be used because we need to take union over all such k. But we don't know that because union of closed sets may not be closed. So that idea cannot be used in this case. So this will be nilpotent, but we need to prove this explicitly. We need to prove that complement of this set is open. Something is not nilpotent means there exists a neighborhood which is okay. Let us see. So this remain open. To try. The set of all matrices in MNC which represent orthogonal projection is closed in MNC. So for this, the set S is given by A belongs to MNC such that A is orthogonal projection. That means A star A is identity and A square is also identity. A square is A. Projection means this is the main thing, and so A can be S can be thought of as intersection of those two conditions. A such that A star A equal to identity intersection A such that A square equal to A. So this is closed and this is also closed. So we just consider this kind of function A goes to A star A, and in this case consider A goes to A square minus A. So this is F inverse 0, this will be F inverse identity. So those are closed. F inverse of singleton set which is closed, therefore closed. So B is okay. What about C? In C, the set of all matrices such that both of their eigenvalues are purely imaginary. So C may not be true because for C we can construct this kind of 0, 1 by n minus 1 by n 0. So those are eigenvalues are plus minus I by n, and that is all those n belongs to uh, this set purely. This is the set S. All those n belongs to S, but its limits is 0, whose eigenvalue are not, so 0 does purely imaginary. So I'll stop here. Thank you.